Okay, finally, I want to briefly share with you some theoretical concepts of how train and test error, actually test error generalization, how it depends on the complexity of your model. And for a simple statistical model like this one, so if you have a linear model with Gaussian noise, you can try to write down the expectation of your test error, and we can calculate it for different training sets. So we can sample different training set from the distribution, from the joint distribution of our x and y, then feed different models using the same set of parameters, say the same value of alpha or the same set of features, and then calculate the expected value of this quantity. And it's a very well-known decomposition. Unfortunately, we do not have time to go through the proof, but it's more or less compact, more or less straightforward. You can see the proof if you follow the link. But finally, it can be decomposed as a sum of three quantities. So the last one is just the square standard deviation of the random noise. It's a constant term, so we cannot beat the noise. And this part is unreducible one. And here we have two interesting terms: bias, squared bias, and variance. And bias is just the difference between the ground truth function and the expected, again, kind of the average model, average in terms of averaging of models created by fitting on different training sets. And this error, this part, can be high if your model is too simple. So if your model doesn't allow you to fit this original function well. The second part is variance, and this part can be high if even small changes in the training sample or small changes in some parameters of your model result in a huge difference between these two models. So it can be, large variance can be a good sign that your model is too complex. So just remember these oscillating polynomials. We just slightly modify the set of training points, slightly move all these points here and there, and we will get a completely different but still oscillating function. And this variance will be really huge. And there is a schematic way to show how these two terms, bias variance and the total error, which is bias plus variance plus noise variance, how does it depend on the model complexity? So for a simple model, we have huge bias. Say, imagine that we have a constant fit or almost constant fit. And this term, this prediction will be very stable, so variance will be low, but the fit, the training fit, so bias, squared bias, can be actually is similar to the training error, the error on the train set, say MSE. For this almost constant fit, the bias will be high, right? You just cannot fit your data with a constant fit. Then, if you move from this part of the graph to this part of the graph, the right part of the graph, here you have really huge variance. Again, remember this oscillating polynomial function, but really high, really low bias. And the total error looks like this curve, and you need to identify the area with the optimal or a complexity near to optimal. So you need to identify these areas. We can compare this theoretical graph with a real one. This is, for example, the graph for our degree experiment. So here we modified degrees. So these green curves, these two green curves, are similar to the black curve from this graph. So total error is more or less equal to the error on the test set. So we can see that, or we can check this experiment. So as you can see, for this simple problem and for this set of methods, the theoretical curve is more or less similar or close to the real ones, but sometimes it's not the case. And let me return to the concept itself. Bias and variance can be visualized in a very nice way. I recommend you to follow this tutorial and to read the explanations, but I really like this image, and it gives a really intuitive explanation of the difference between high bias and high variance. So imagine that you are a sniper, and if you have low bias and low variance, then all your shots will be near the central point. If you have high variance, that the average of your shots will be somewhere still near the right central point, but the mean distances will be higher. And similar, for high bias, you still have a really close point. For high bias and low variance, you still have a really compact set of points, but this set of points is shifted from the right target. And finally, for high bias and high variance, you have really a combination of these two types of errors. So I recommend you to follow this, to check this blog post for further discussion on the topic. Okay, yeah. And finally, you can try to estimate bias and variance at home, just to write down some formulas, because here within this plot we just used train and test errors, and actually it's not identical to the bias and variance, just because here we had only one training sample, right? And we calculated these values for one particular model. And in the definition of bias and variance trade-off, we have expectation, and to calculate this expectation we need to generate a lot of samples and to generate a lot of models for one particular value of complexity. And the final point is that this concept, I mean bias-variance trade-off, is a simple one and a nice one, and many real models and real problems, models applied to real problems, follow this overall trend. But for some types of methods, especially for deep neural networks, the situation is different, or even completely different. So there are some other approaches on explaining how generalization depends on the complexity of your model. And for example, there is a quite recent concept which says that actually we have two regimes. One is kind of classical one for classical models like linear regression or I don't know, k nearest neighbors, etc. And there this test risk or test error or the total error in terms of bias-variance trade-off looks like actually exactly like we plotted in our experiments. So it's kind of like a parabola. And training risk just goes to zero. But then when we move further and we create too complex model with too many parameters, that it's more than we need to interpolate all the training data, even more parameters. And in this case, the overall test risk, test error in this area again decreasing. And the majority, or actually all the methods we will discuss during the course belong to this part of the graph. And some modern methods like deep neural networks are here. So there is again a nice discussion here. You can just go through, and there are some early examples of abnormal behavior. I mean abnormal in terms of these classical curves. And also there is a link to the paper describing this idea with more details. So if you have, say, 30 minutes, I highly recommend you to follow the link.